morning friends. In chapter 12 thermodynamics we already discussed about zeroth law of thermodynamics, right? Okay, now the state of a system is explained or described by its state variable like as the pressure, volume, temperature, amount of the heat and also internal energy of a system, right? On the base of this, today we are going to discuss about what is the internal energy, and internal energy of a system depends on what. And also we are going to discuss about the first law of thermodynamics, right? Okay. Now our question is that explain internal energy of a system. Explain internal energy of a system. Now, we know that every system consists of a large number of molecules. Here we consider the gaseous system. So, gaseous system is made up of the numbers of molecules. And internal energy is the sum of kinetic energy and potential energy of the molecule. Again, the internal energy is the sum of kinetic energy and potential energy of the molecules. In thermodynamics, the kinetic energy of the system is not relevant. There is no importance of the kinetic energy of the system in thermodynamics. But the internal energy is the sum of kinetic energy plus potential energy of a molecule. There is not a kinetic energy and potential energy of a system. Keep in mind that internal energy is the sum of kinetic energy of molecule and potential energy of a molecule. In thermodynamics, the kinetic energy of the system is not relevant, is not important. Thus, internal energy associated with random motion of the molecule of the system. Already in earlier chapter, we discussed about that. The gas is made up of the numbers of the molecules. And this molecule performs the random motion and obeying the Newton's laws of motion. So as a result, the internal energy associated with the random motion of the molecule of the system, because the system is made up of the numbers of molecules, and this molecule performs the random motion, and therefore the internal energy of the system is associated with random motion of molecule of the system. Internal energy is macroscopic variable of the system. It depends only on the state of the system, not on how the state was achieved. What it says that the internal energy is macroscopic variable, is very small variable. There is no directly measurable physical quantity. Now keep in mind that, like as the pressure, volume and temperature, we directly measure. But the internal energy of a system not directly measured. There is a physical quantity but not directly measured by self. That is the depends on other physical quantity. By knowing the other physical quantity, we can know the internal energy of a system. It depends only on the state of the system, not on how the state is achieved. In whatever the state the system is lying, on this state, the internal energy of a system is depends. Right? Okay. Now, thus the internal energy of a given mass of a gas depends on the state described by the value of pressure, volume and temperature. Thus, internal energy of a system of a gas depends on its state. This state described by the specific value of the physical quantity pressure, volume and temperature. So in short, we can calculate or we can know the internal energy of a system by knowing the value of other physical quantity pressure, volume and temperature of a gas. State of thermodynamic system is characterized by its internal energy but not by heat. Initially the system is in which state? This state is described or characterized by its internal energy, not by the heat. Whatever the heat possessed by the system, on the base of the heat, we can't describe the state of a system. But by knowing the value of the internal energy of a system, we can explain the state of a system. In short, heat and work in thermodynamics are not the state variable. Heat and work are not state variable. They are modes of energy transfer to a system resulting in change in its internal energy. What it says that the heat and work are not the state variable, but they are modes of energy. Heat and work are the modes of energy transfer to a system resulting in change in its internal energy. Due to the work done or the heat absorbed or the heat released by the system, the internal energy or the state of a system is changed. Right? Therefore, the heat and work are the process of the exchange of the heat. But these are heat and work are not the state variable. That means the state of the system not characterized by the physical quantity heat and work. They are mode of energy transfer to a system resulting in change in its internal energy or the state of a system. So that is the note about the internal energy. Again we repeat it. Every system consists of large number of the molecules. Any system, either the solid or the gaseous or the fluid system, that is the made up of the large number of the molecules. Internal energy is the sum of kinetic energy and potential energy of the molecule. Internal energy is the sum of kinetic energy and potential energy of these molecules. In thermodynamics, the kinetic energy of the system is not relevant. There is no importance of the kinetic energy of the system in thermodynamics. Thus, internal energy associated with random motion of the molecule of the system. Therefore, the internal energy is, or that is the relate with the random motion of the molecule of the system. And internal energy is a macroscopic particle or macroscopic variable of the system. Internal energy is macroscopic variable of the system. It depends only on the state of the system, on how, not on how that state gas is seen. Again, the internal energy is the macroscopic variable of the system. It depends only on the system state of the system. It not depends on how the state was achieved, how the system come into this at present state. The internal energy not depends on this, but at present in which state the system is lying, on this state the internal energy depends. Okay. Thus, internal energy of a given gas depends on its state, described by the specific value of pressure, volume and temperature. So in short, internal energy of a system depends on or described by the specific value of pressure, volume and temperature. State that thermodynamic system is characterized by its internal energy but not by the heat. The state of a system is characterized or described by the internal energy, not by the heat. And thus, the heat and work in thermodynamics are not state variable. Heat and work are the mode of energy transferred to a system resulting in change in its internal energy. So as the heat transfer, the work done by the system or on the system, so the state of a system is changed. So as a result, the internal energy of a system is also changed. Clear this? So there is the importance of the internal energy in thermodynamics. Now after that, write and explain the first law of thermodynamics. That is the most important for theoretical purpose, and also that is the most important equation in thermodynamics. As we supply the heat to the system, how much work done or how much change in internal energy of a system take place, that is described by this first law of thermodynamics. Now, the internal energy of a system can change through two modes of energy transfer, the heat and work. Just earlier we discussed that the heat and work in thermodynamics are not the state variable. They are mode of transfer of energy to a system, and as a result to change the internal energy of a system. Thus, the internal energy of a system can change through two modes of energy, heat and work. Suppose delta Q is equal to heat supplied to a system by the surrounding, and delta W is work done by the system on the surrounding, and delta U is equal to change in internal energy of the system. Again, we are going to discuss about the first law of thermodynamics. At that time, the internal energy of the system depends on the heat and work, but the heat and work are not a state variable. Right? Heat and work are the modes of energy transfer to a system. So as a result, the change in internal energy takes place. Therefore, the internal energy of a system can change through two modes of energy, heat and work. As the heat and work transfer, so the internal energy of a system can be changed. For that purpose, we assume that suppose delta Q is equal to heat supplied to the system by the surrounding. That means the heat is supplied to the system by the surrounding, and delta W is equal to work done by the system on the surrounding, and delta U is equal to change in internal energy of the system. So as a result, from law of conservation of energy, delta Q is equal to delta U plus delta W. So whatever the amount of the heat supply, so partially used to do the work done, and remaining is utilized or used to make the change in internal energy of a system. Again, whatever the heat is supplied to the system by the surrounding, this heat is partially used to do the work by the system, and remaining part of the supplied heat energy is used to change the internal energy of a system. That means to change the state of a system. Therefore, delta Q is equal to delta U plus delta W. What is the delta Q? It's supplied to the system by the surrounding. What is the delta W? Work done by the system on the surrounding. And what is the delta U? Change in internal energy of a system. Okay. Now, this equation is known as the first law of thermodynamics. Equation 1 is known as first law of thermodynamics. And from this equation, delta U is equal to delta Q minus delta W. How the internal energy of a system or the state of a system depends on the heat and work. We are going to discuss this thing. For that purpose, from equation 1, this equation, energy delta Q supplied to the system goes in partially to increase the internal energy delta U of the system and rest in work done by the system. Here, delta Q is the heat energy or the energy supplied to the system. This delta Q goes in partially to increase the internal energy delta U of the system and rest in work done on surrounding delta W. Therefore, delta U is equal to delta Q minus delta W. Thus, delta Q is equal to delta U is equal to delta Q minus delta W. What is the meaning of this equation? Initially, we discussed about that the internal energy represent the state of the system. As the state of the system changes, so the internal energy of a system also changes. So here it represents delta Q is the change in internal energy is equal to delta Q minus delta W. Okay. To change the state of a gas from P1 V1 to P2 V2. Initially we have the one gaseous system having the pressure is P1, volume is V1. There is the initial state of a gaseous system. We want to bring this system into the another state in which the pressure is V2, volume is V2. So here the three different ways we can bring the gaseous system from initial state in which the pressure is P1, volume is V1 into the final state in which the pressure is P2, volume is V2. The first way is that change the volume of a gas from V1 to V2 keeping the pressure constant. First we keep the pressure constant and we bring the system from volume V1 to the volume V2. That means we make the change of the volume of the system from V1 to V2 keeping the pressure constant. Second way is that change the pressure from P1 to P2 keeping volume constant. Second method is we are making the change in pressure from P1 to P2 at constant volume. Constant volume. Okay. And third way, by changing the both volume and pressure, we bring the system from P1 V1 state to the final state P2 V2. Now to clear a concept, just here we do the graph of the pressure and volume like this way. We discuss this graph in next. There is the pressure, there is the volume. There is the initial state. Here the pressure is P1, volume is V1. We want to bring in the next step P2, V2. That is the second step, final. So here the one way is we make the change in volume from V1 to V2. So here the volume is V1, here the volume is V2. At constant pressure. So pressure is constant, we bring the system from P1 to V1 to V2. Second method is change the pressure P1 to P2, keeping the volume constant. In second method, we bring the system from, that is our P1 pressure, and that is our P2 pressure. We bring the system from P1 to P2 at constant volume. That is the second method. And third way is that by changing the both volume and pressure. Third way is this. Both changing simultaneously. We discuss about this gap in next. Work done for the isothermal process. Right? Okay. Again, to change the state of a gas from P1 V1 to P2 V2, here are the three different ways. First way is that first change the volume of the system from V1 to V2 and keeping the pressure constant, and then change the pressure from P1 to P2 keeping the volume constant. And third way is the changing the both volume and pressure to take the gas into the second state P2 V2. This gap is not important here, only for understanding. Okay. When the system is taken from one state to the second state, So what's happened? The delta Q and delta W are different for different path. Here the three path to take this. One path is this, second path is this. We keep the pressure P1 to P2 at constant volume. And first method is to keep the pressure constant, we bring the system from V1 to V2. So one path, second path and third path. For all these three paths, the delta Q and delta W are different for different path. Right? Means delta Q and delta W depends on the path, but difference delta Q minus delta W is constant for all these paths. Yeah? Yes, we bring the system from initial state P1, V1 to the P2, V2. Here we can take the three paths. One is make the change in volume at constant pressure, this first path. Second, keep the volume constant, we change the pressure P1 to P2, that is the second. And third, changing both volume and pressure. So three different ways we bring the system from initial state P1 to final state P2. For this third part, the value of the delta Q and delta W, that means the extent of the heat and work done on the surrounding are different. But the difference delta Q minus delta W is same for every path. And that depends on delta Q minus delta W is depends only on the initial and final state of the system. Again, the delta Q minus delta W is same for all these paths, but it depends on the initial and final state of the system. That means the change in internal energy of a system. Therefore, the delta Q minus delta W is equal to change in state of a system. That means the change in internal energy of a system. Therefore, first law of thermodynamics is change in internal energy is equal to delta Q minus delta W, and that is the first law of thermodynamics. Clear it? Again, just to repeat how we bring the system or how we make the change in state of a system. So here, first law of thermodynamics is delta Q is equal to delta U plus delta W. To change the state of a gas from P1 to P1 V1 to P2 V2. Here the three different ways. First way is change the volume of a gas from V1 to V2, keeping the pressure constant. Second is, so here first we make the change in volume V1 to V2 at constant pressure. Second is to make the change in the pressure P1 to P2 at constant volume. And third way, by changing the both volume and pressure, and the gas bring to the final state P2 V2. Okay. When the system is taken from one state to the another, the delta Q and delta W are different for different paths. Here the three different paths to bring the system from P1 V1 to the P2 V2. For this three paths, the value of delta Q and delta W are different. But the difference of delta Q and delta W, it means delta Q minus delta W is same for all the paths. This difference depends on the initial and final state of a system. It means that is the depends on the change in internal energy of a system. Thus, the first law of thermodynamics is delta U is equal to delta Q minus delta W. Clear this? So that is our discussion about the internal energy and also first law of thermodynamics.